Hi, and welcome to our next session here. This is a very brief session on the elastic net, and I guess I'm also nearly losing my voice. So in this session here, we'll just figure out that instead of just using L1 and L2 separately as penalties, I guess we can also combine them. There's always kind of an obvious thing to try out in these types of situations, and yes, that works. We can kind of get the best out of both worlds through this combination, and this combination is usually called elastic net by people. For some more or less, I don't know, arbitrary reason, I've also included one slide here on regularized logistic regression, so we can see that we can also use regularization in the same manner with basically the same properties, not only on top of linear regression models, but also on top of linear classifiers like logistic regression. So let's start with the elastic net. You can also take a look at this here, at this paper here, if you want to learn more details, but I guess the thing in general is not too difficult to understand. So like I said, now we are not only adding in L1 and L2 separately, but we add them in both. So now they have a control parameter, each by themselves, to control their respective strength. Okay, so we have a lambda 1 and a lambda 2, so I guess it's a little bit more hyperparameter optimization than just selecting one through cross-validation and whatever hyperparameter optimizer you like to use to do efficient selection here. Again, you can do things like full path computations to speed things up, at least for the linear model. Okay, the second formula here on the slide simply says that you can rewrite these penalties, the sum of these penalties, in a different way. This is really straightforward. So this second form here just kind of reparameterizes things, as you can see here, okay, like that. Now with an alpha parameter and a lambda parameter without an index. So the only reason we do this is that this allows a somewhat more convenient interpretation of things, especially if we then computationally optimize lambda and alpha, so we kind of understand a little bit better what their optimal values mean. So here the alpha value actually controls the portion of the L2 penalty. So this is, it's between 0 and 1, right? So alpha in a certain sense is the percentage of L2 we mix in, and 1 minus alpha is kind of the, percentage of L1 we mix in. And then there's the lambda parameter, which kind of controls the global strength of the combined penalty, okay? Simple reparameterization. What happens under correlated features for elastic net? Well, they either tend to be selected together or zeroed out together. So that's usually what happens. For elastic net, it is now actually possible to select more than n features if p is larger than n. So in these higher dimensional spaces, we did at least mention that this wasn't possible for the LMU, so that's, I guess, an advantage here. Here's a short simulation example to demonstrate its properties empirically. I guess it's actually two examples. So two situations, let's call it like that. So I have again used a straightforward linear DGP, data generating process, to simulate things from I have sampled always 100 observations. I've actually created 50 different data sets to kind of also do, a variance analysis of things, and creating a certain correlation structure for my features, because that's, I guess, what I want to study here. So maybe it's actually even easier to start with the scenario here on the right-hand side, so you can see the true theta vector here, and you can see that there are only 3 informative features, the first 3, and they have a true coefficient of 2, and then there are 7 features in there which have a true coefficient of 0, and the correlation structure is now, there is no correlation between the features, okay? So the sigma matrix here, that thing is the identity. So all features are uncorrelated, and because it's Gaussian, they are independent. Now, on the left-hand side, I'm creating a correlation structure. Again, this triplets structure that we used before, and what can we now see? So for this case here, so for the uncorrelated features, where the true structure is also quite sparse, right? Only 3 of the 10 features actually have an effect. LMU works better than rich, which I guess we expected, because we really have this true underlying sparse structure and there is no strong correlation to screw around with the LSU. In this case here, with the correlation, and where the underlying structure is a little bit less sparse, I guess it's more the correlation than having two more features in there in the DJP, ridge actually works a little bit better. But what we can also nicely see is that if we use elastic net, especially with automatic hyperparameter selection for cross-validation, this works quite well for both cases. So at least in terms of predictive performance, which is what we are looking at here, I'm pretty sure we computed this again from repeated cross-validation. We can also peek a little bit more into the estimated parameters. So if we care about feature selection and so on, are the correct things selected here? We couldn't really see this from the slide before. I mean, we probably had a suspicion that it works better for the models who are better in prediction, but this is not necessarily true, right? So on the left-hand side, so here we have this correlated case, and here we have this uncorrelated case. Okay, I guess that's barely readable, what I'm scribbling on the slides. So on the left-hand side, we can actually see that the ridge regression doesn't really do feature selection. Discussed this before, not very surprising. Feature vector is basically dense. If you look at LSU and elastic net, remember there were 5 features in there, these 5 guys, which had a true effect of 0. It's not perfect, it doesn't work in all cases, but it works, yeah, approximately fine. The LSU sometimes, more frequently, ignores relevant features than elastic net. So we can see these slightly elongated tails in the violin plot of the last 5 features, but actually no, it ignores relevant features a bit more, which you can more see from this here, right? So some of these features, these are the informative features, are sometimes estimated to 0. That happens a bit more often than in the elastic net case, but it doesn't happen too often. If you now look at the right-hand side, we can see that our ridge estimates, so our L2 estimates of the noise features, they hover around 0. They are not estimated exactly to 0. I guess you can see this a little bit less well from this. Well, I guess you can see it from this plot, and you should definitely see that LSU and elastic net handle these 7 noise features better. Now they more often shrink them to exactly 0. And again, you can see if you just focus on the first row that elastic net, well, works quite well in both scenarios. Final slide. We're already done with this session here. Regularized logistic regression. It's also nicely a super simple slide because I only want to tell you that you can add penalties to basically any model based on an empirical risk minimization, even on top of nonlinear ones, but these we'll discuss in a separate dedicated section. So here for logistic regression, there's really not that much to say. We can just add the penalty into the GLM, okay? We can create L1 or L2 penalized logistic regression. I guess we can do an elastic net for logistic regression too. We can achieve the same things, so we can guard against overfitting with that linear model, especially in high dimensional spaces. We very often like to do feature selection with the L1. We could use the SCAT, we could use the MCP, we could use the elastic net together with logistic regression. I have at least produced one super simple example here to show how that maybe feels like. And what I also want to kind of show here is that, I mean, sometimes we also say that regularizing the model makes the, I don't know, the response surface in here, especially the decision boundary for classifiers, more smooth. And I wanted to show that. So in order to show that, I now used actually 2-dimensional data, but I didn't really want to have a truly linear model and a linear decision boundary. So I want to have something that's a bit more wiggly. So now I created polynomial features on X1 and X2 up to degree 7. So interaction effects and higher order effects for X1 and X2. And then so in a certain sense, I don't know, I over-parameterized I made it somewhat flexible for this 2D case here. And the data looks like, so there's a class 1 in such a circle, and then there's class 2 on the outside of things, okay? So the idea is that I have to fit like this circular structure as a decision boundary, to perfectly separate, or to kind of to get the decision boundary, which is, I guess, base optimal. Yeah, let's phrase it like that. And I've now used an L2 regularized logistic regression with different lambda values, and you can see what happens. If I don't regularize, I get a pretty wiggly decision boundary. So it's more rough. Yeah? Remember that we also called the penalty maybe a roughness penalty on the model, and this is where this comes from, right? So you get a pretty rough decision boundary, pretty wiggly. And the larger we make lambda, the more smooth it becomes. Here I stopped at a lambda value of 1, which is pretty much optimal, I guess, for this situation. Okay, this ends this brief session here. Hope you enjoyed this. See you in the next one. Goodbye.